Our last day of school is the 25th.
Yeah, your final is only for 3 days, Monday, Wednesday, Friday, right before Thanksgiving, to the week of Thanksgiving. So maybe some of you have to take 2 or more than 2 a day. You have 3 a day.
I'm pretty sure I have both my math ones on Tuesday.
You.
Yeah, I think so.
Hopefully there's some time gap so you can study
Yeah.
for the next one. Alright. Yeah. Okay, by the way, scientific notation. Does anybody remember anything about scientific notation? How do you write the scientific notation?
You always multiply it by 10 to a certain power.
Right, power of 10 is important, but the number in front of it is really important too, right? So what do you know about that?
It needs to be in between 1 and 10.
Between 1 and 1, including 1, right? Including 1, but not including 10. So greater than or equal to 1, let's say A, and the number should be less than 10. So 9.57, that's okay, but 10 point something you can't. So that number times 10 to the some power. This is the form for the scientific notation. So for example, is this scientific notation? 0.5 times 10 cubed. Is this scientific notation? Some goes like that, some goes like that.
You
So
can't have a
think
decimal.
about that again. Think about that again. You can have decimal, but this number is less than 1, right? So how do we change this to scientific notation?
Could you do 5 times 10 to the second?
Oh, so this one, 0.5 is 5 times 1 over 10 or 5/10, right? 5/10 is 0.5 and I have times 10 cubed. So if you take a look at this, what happens? 4 or this is in the denominator, that's in the numerator. So if I rewrite this again, it's going to be 5 times 10 cubed, 10 times 10 times 10 over denominator 10. What can we do?
You can take one of the 10s out.
You can cancel those out, right? And you have 5 times 10 squared. So you have 5 times 10 squared. This is your scientific notation. That 5 is between 1 and 10. So yes, this is scientific notation. Okay, that's one example. We're gonna do a little bit more of the practices, but just to review. How about this? Let's use similar problems. 53 times 10, let's say, to the negative 5th power. Do you think this is scientific notation?
Is that 53 or
53. Let me use the whiteboard. You can see better. Okay, what I wrote here is 53 times 10 to the negative 5th. Is this scientific notation? No, it's not. Why? Why not? I see power of 10 here, so this part is okay. However, this part is greater than 10, right? So you can't. You need to change this. How?
5.3 times 10 to the negative 4.
Oh, so 53 is the same as 5.3 times what?
10 to the negative 4.
No, just looking at this. 53. 53 times what? 53 is equal to 5.3 times what? How do I change 5.3 to 53?
Times 10.
Times 10. So 53 itself is 5.3 times 10. Do you agree? Which is only this part, right? So I can rewrite this as 5.3 times 10, which was this part, times, I already have this one as well, so 10 to the negative 5th power, right? Now I have power of 10 here and there, right? Here and there. How do I combine them? This is 10 to the 1's power, right? 10 to the 1 is 10, 10 to the negative fifth power, which is 10 to the what power?
-4.
Negative fourth. You can just add them together in multiplication with the same base. Or if you don't remember that, you can do it this way. 10 times 10 to the negative fifth power is 10 times. Negative power is what? 1 over, right? 10 to the fifth power. If you want to simplify this, you can do 10 times 1 over 10 to the fifth is 10 times 10 times 10 times 10 times 10. So you can simplify these two and having 10 to the fourth in the denominator, right? 10 to the fourth to the denominator, I need to move space here, but that is the same as 10 to the negative fourth power. Do you agree? So this whole thing is 10 to the negative fourth power. So the scientific notation for this should be 5.3 times 10 to the negative fourth power. Okay? So I gave you some of the examples, and I'm pretty sure you can do more of those similar problems. So for example, well, these are the scientific notation. As you can see, 8.3 is greater than or equal to 1, but less than 10. Same for 1.2, it's between 1 and 10. Look at this, even negative number, you're gonna look at negative value between negative 1 and negative 10, okay? So we're looking at the absolute value of that. And 7.84 is between 1 and 10 as well, right? Okay, so we're good. Now, let's write these in scientific notation. So I want everybody to try this on your notebook. So for Brennan, I can write down the problems here. Oh, 413. 400. 413,682,000. Shall we look at this together? Let's take a look at this together. We know this number is way too big. What we need for our scientific notation is a number between 1 and 10 times 10 to the some power, right? So let's find it out. Well, if you change this to a number that is between 1 and 10, what can that be? It has to be
4.1.
4 points. Exactly 4 points. Rest of them, just write it. 682. I'm just gonna put it blank here. Yeah, so 4.13682 is from this original number, and it is greater than or equal to 1, but less than 10. So this is a good number, but it has to be equal. How can we change this to equal? Does anybody have an idea?
You put 10 to the 8th power.
How did you find 10 to the 8th power?
Count how many
Yeah,
times the decimal
so-
place was moved.
There we go. So our decimal point here is hidden because this is a whole number. There's no number on the right hand side of decimal, right? So this is 413,682,000. If you move this decimal point all the way to here, let's see how many digits we have moved that decimal point to. We have 1, 2, 3, 4, 5, 6, 7, 8. We moved that to 8 digits, right? So it's gonna be 10 to the 8th power. How do you know it's positive 8, not negative 8? Because we have to make this number really big. If you put negative 8 there, you are dividing this by 10 to the 8th power, by million, 100 100,000, I mean 100 million, right? 100 million, so it's way too small then. So you need to make sure to make number bigger like this from 4.13682. You need to multiply this by positive exponent. Okay? Does it make sense? Let's look at the next one. It's opposite. So when you're looking at B, okay. So if you are doing B, it's 0.0000231. Is this a big number or small number? Small number. So originally, I mean, automatically we get to know, oh, that 10 to the power, that should be positive or negative? Negative, because we have to make this really, very small from 2.31. This is bigger number. How do you make it small? We need to divide that by 10 to the some power. So it should be negative power. Okay? So let's see how many decimal points we have to move. We can put 2.3 here, right? And count how many points, decimal points we have to move. We did 1, 2, 3, 4, 5, right? It's going to be negative fifth power. Are we good? Okay. Let's do part C together as well. Now we'll let you do D and E. C, 83.7. How do I change that to scientific notation?
8.37
Oh, I
times
love it.
10.
Times 10 to the, you need to make this number bigger, right? So it has to be positive exponent. By how much? It's 1, because we move this 2 on 1 decimal point here, right? So just 1, which is the same as 8.37 times 10. Either one is okay because they are the same, okay? Okay, your turn. How about D and E? D and E. He is like that. Can I have volunteer who can write that on the board, either side? I need 2 volunteers. No volunteer?
Which board do you want it on?
Either board? Thank you.
Do you have a marker now?
Yes. Yeah. Thank you.
Yeah, it doesn't matter which one, or do you want me to do both?
Oh, it's whatever you like to do.
I'll do E.
E, okay. We're gonna start from E. Is there any volunteer for D? Not really. 334 times 10 to the negative 6 power. Oh, I like the big handwriting. Yeah, I think it's essential for classroom teaching too. That was my teacher. All right.
I think you're right.
I'll do the big one.
100.
Okay.
What are we doing here? We're changing the number to scientific notation.
it's already in scientific.
It's already in scientific.
Is that a scientific notation?
You gave me this one. So
Uh-huh.
then
Is that scientific notation?
The number has to be between 1 and 10.
Oh, but it's negative, so aren't you making it smaller?
I think you're confused. So you thought this was a scientific notation, first of all, right?
Mm-hmm.
This is not. Why? Look, 0.34 is not bigger than 1.
Oh, so I'm gonna make this
Yes.
3.4.
Exactly.
And then the 10 to the.
They may be the
negative.
same. They may be the same. They are the same, but this is not a scientific notation.
Okay, so then I have to make this 3.4.
There we
times
go.
10 to the negative 3.
Negative something. You need to figure it out.
I thought I just had to reverse it.
Not yet.
Not
You
yet.
want to finish it?
Well, yeah, but I'm gonna erase it.
Okay, yeah, this is eraser.
Yeah, no, I don't think it's gonna come out very well.
Yeah, I think
Maybe
this
like
is
a
so
spring
bright.
or something.
Yeah, but the lady comes only once a day in the morning. There we go, there we go.
And then just move it.
Right? Can you do a little bit more there? How did you find -5 there?
Well, I knew I had to move the decimal place back 1.
So you meant,
So then I just did 5 minus, I think 6 minus.
so this is 3.4 times 10 to the what power?
To the, this one.
No, this one, only look at this part. This is same as, I'm asking everybody, 3.4 times 10 to the what makes 0.34?
Negative 7.
No, just look at this part.
Oh, that.
Just 0.34 to 3.4.
Negative 1.
It has to be -1 to that, right? But you already have times 10 to the -6 power. So what is that? Finish that.
Oh, so you add
-1, -6.
Oh, so you're adding to the negative.
There we go. There we go. Okay, so you tend to make mistake if you just look at this part and find the exponent. Me too. It's not easy for me either, right?
Yeah.
But if you extend this 0.34 to the 3.4 times 10 to the -1 power, you can obviously see what's the exponent for the power of 10.
Okay.
Okay, so try to do this way instead.
This way, okay.
Uh-huh. Sounds good?
Yeah.
Thank you so much,
I
Isabella.
think it's 3.4 to a positive 10, because you put the decimal into.
Okay. Now here's the debating. What's 3.4 times 10? You're
Oh.
making this number bigger.
Yeah, okay, so it'd be 0.34 times positive 10. To get to 3.4.
Then it becomes 34. But we have to make these two equal.
Right, but
So-
if you bring the decimal in between 3 and 4, wouldn't it be 10 to the -5 at the end, so 10 to the -7?
No, look. So 3.4 is bigger number than this, right?
Yeah.
To go to original number, you need to make this number smaller. So you need to divide this by 10, which is times 10 to the -1 power. So these two are exactly the same.
But when you put, so if it's 0.34 and you move the decimal to 3.4,
Mhm.
wouldn't it be technically 10 to the -5? And then once you add it, once you multiply by 10 to the -1st, it'd be 10 to the -6.
No, you need to make these two equal. So you need to think about 0.34 is, this is 3.4 times 10 to the -1 power. But we tend to make mistake there. We think 3.4 times 10 is 0.34. No, 10 to the -1 is 0.34, right? So I strongly encourage you to write equivalent decimal here with a 10 to the something power with a 3.4, okay? That scientific notation, then multiply that by 10 to the -6. So you reduce your mistake there. Okay, does it make sense, everybody? Okay, so that was a very tricky one. How about the last one? If there's no volunteer, I will write it here so I can record it. Okay, so D, let's look at D. How do we write this? We need to change this to a number between -1 and -10. So we need to change this to -1, right? So decimal point moves to all the way here. Let me use the red color. Okay, decimal point was here. Why does it keep doing that? Decimal point was here, but now we're gonna move that to here, right? So how many decimal points do we have to move? 3, 6, 7, right? So -1 times 10 to the, is it +7th or -7th? +7th. So we are making this number really, really big in absolute value. Okay? I'm actually so glad that Isabella did a little bit differently, because that's our mistakes coming from. Everybody actually thought about that way. It's not only you, right? Everybody else did that way too. So that was really good. Let's look at the next example. Convert the following to standard numerals. 6.84 times 10 to the -5. So this one is already given as scientific notation. Now you are looking for standard numeral that Isabel was looking for at the beginning.
Can you share your screen, Professor Colin?
Oh, if we work on that,
I think Brandon was trying to talk.
Brandon,
I think so, yeah.
Brandon, do you have anything to talk?
Can you share your screen?
Yeah. The problem is I cannot share the screen and the whiteboard at the same time. But this screen, you can find it on our Google Notes. Okay, can you see now?
Yeah.
Okay. So now you are given scientific notation. As you can see, all of these numbers in front of the power of 10, 6.84 is between 1 and 10, 3.12 between 1 and 10, -4.08 is between -1 and -10. So they are scientific notation, right? Change that to the standard numeral. Okay? Okay, are you done? How many of you are done? Okay, so let's take a look. Do you think this number will be smaller than 6.84 or bigger than 6.84?
Smaller.
Smaller, because we are multiplying that by 10 to the -5, which means multiplying by 1 over 10 to the 5th, right? So if you don't remember, or if you don't know how to do that, you can think about changing 10 to the -5th power as 1 over 10 to the 5th power. You can think about this way, right? Which is 6.84 over 10, 100,000 with 5 zeros, right? 10 to the 5th power. So we are dividing 6.84 by 100,000. So we're gonna make this number smaller by how many decimal points?
5.
5 decimal points. So do we move this decimal point to to the left or to the right?
Left.
Left. If you move to a decimal point to the left, the number was really, really small, right? 0.00 something something. So from here, we can move the decimal point 5 decimal points. That's annoying. Okay, 5 decimal points. So 1, 2, 3, 4, 5. Okay, and it goes point here. What do we do? What are we gonna do with all of these spaces here?
So it was zeros.
You're gonna put placeholder zeros there. 0, 0, 0, 0. And decimal point is here. So the answer is 0.0000684. Right? You can check this answer by just going backwards. How can you find the scientific notation of this number? Well, we know we're gonna move this decimal point here, 6.84, right? So we can say it's gonna be same as 6.84. Just cover original, okay? Times 10 to the what power? 10 to the 1, 2, 3, 4, 5. Is that 5 or negative 5? Because we are making this to the smaller number, it's gonna be negative fifth power. And compare this with the original. Yes, they are the same. So your answer was correct. Okay? How about this one? 3.12 times 10 to the 7th power. Are you making this number bigger or smaller?
Bigger.
Bigger. By how many digits?
7.
7 digits. So you can just move decimal point
To
to
the
the
right.
left or to the right?
Right.
Right, by 7. 1, 2, 3, 4, 5, 6, 7. Decimal point goes here, and the rest of them we can fill up the spaces with placeholder 0. So your number should be 3, 1, 2, 5 zeros. 1, 2, 3, 4, 5. Right? If you want to put commas there to read it easily, you can put commas there. And read this as 31 million
200,000.
200,000. There we go. How about this one? Negative 4.08 times 10 to the 4th power. This number goes bigger in absolute value or smaller in absolute value?
Smaller. Smaller. It technically goes smaller.
Technically, I say absolute value.
Oh.
So
Bigger.
it's bigger, right? So disregarding the negative number, we know that's negative. Technically, so it is actually getting smaller, but we are looking at the absolute value of that. So it's gonna be 408. We are moving the decimal point to the right by 2 more and putting the zeros in the placeholder. So it's gonna be what? Negative 40,800. Okay. Any question for this? Are we good? I think so. All right. So, where did I go? I need to share this one. Okay. Now let's do some division. Here is a word problem of division. Okay. Michelle purchases several bottles of water. Before tax is added, the total cost is $3.60, and the cost of each bottle is $1.20. How many bottles did she buy? How can you find that? She paid $3.60, and each one cost $1.20. And she needs to find out how many bottles she bought.
You divide.
You're gonna divide the total cost by each bottle, right? And find out how many bottles. If you use the model, can we do it this way? And say, this is $1. If you see a square there, that's $1. That's another square, another dollar, another square, another dollar. So I have $3. The fourth one, I don't have the whole, but I have only 60 cents. So you can see that, well, each square can be broken into 10 equal pieces. So if this is $1, only 1 part out of 10 has to be how much? If this whole thing is $1, this square is $1, 1/10 of that should be 10 cents, right? So I have 10 cents, 20 cents, 30, 40, 50, 60, 70, 80, 90, 100 cents, which is $1. Do you see the representation? Can you interpret that? So we have $1, $2, and another square, $3. So we have only 60 cents. So we don't have the $4 there, but we have only 6 bars, which represent 60 cents. So regardless of the color, the shaded part is $3.60. Okay? $3.60. We are dividing it by $1.20. So each group has to have $1.20, and we're going to find out how many groups, which is how many bottles, right? So I see $1.20, that's one bottle, purple bottle, and I have another 8, 9, 10, 11, 12. So $1.20, that's the second bottle, and I have another 12 bars, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 bars, $1.20. That's the third bottle. So I know there are total 1, 2, 3 bottles, right? That's how you can find it. But do you want to always use the model like that? Maybe for the younger students, it's better for them to understand what's going on. But for the convenience, it's better for us to know how to divide it, right? So using the long division, because we know we have to divide 3.60 by $1.20, you can think about this as power over 10. Because for us, it's easier to divide 36 by 12. Going back to this model, instead of we are counting this as 3.6, it was easier for us to look at this whole thing as 10, 20, 36. 36 divided by 12, right? That was easier. So we can change the decimal to the whole number. It's so much easier. So we're trying to do that, okay? That's what I'm saying here. And it also makes sense because if I write it here, we know 3.6 divided by 120 can be written in fraction. How do I write this in fraction? 3.6 divided by 120, right? So the dividend becomes the numerator, the divisor becomes the denominator. Can I multiply same number on the numerator and denominator? Does equality change? It doesn't change, right? If I multiply this whole thing by 100, I can do the same thing to the denominator, but the equality doesn't change. It's equivalent, right? We have learned that in fraction. So I can change this to 360 divided by 120. That's why we can multiply same number on the numerator and denominator to change the dividend or divisor both to the whole number. Okay, we can do it. The key is if you have, let's go here. If you have instead of 3.6, let's say you have something like I'm just making it up, divided by 3.5. Let's say you are dividing 36.678 by 3.5. In fraction, this is the same as 36.678 divided by 3.5. What do you want to multiply in the numerator and denominator to to make this easier division. What do you want to multiply? There should be two things, right? 10 or 1,000. Which one do we want to multiply that by? 1,000? If you multiply 1,000, what happens? Let's see both of them, okay? If you multiply this by 1,000 and this by 1,000, it's still the same, equal. We have 36,678. You move the decimal point to the right by 3. So the same thing here. What happens? 3,500, right? So you can do 36,678 divided by 3,500. You can do it this way, or you can multiply this whole thing by 10 instead. Okay, so I have this number. Instead of that, I'm going to multiply this by 10 and this by 10. Still the same, right? If I do it this way instead, what do I get? 366.78, right? Divided by what? 35. Take a look. We're going to compare these two. This is 366.78 divided by 35. Right? By 35. So, comparing these two, which one is easier for you? You divide this by 3,500 or you divide this by 35? Which one's easier? Which one is easier? You can do either way. You're going to get the same answer. But which one's easier for you? Dividing by 3,500 or divided by 35? Which one's easier for you?
35.
Is it? How about for you, Ruben?
I think 35.
35, Yesenia? 35? Isabella? 35? 35? 35?
I think it's just easier to keep track of the decimal.
Because we have to think about 33,500 times 1, how many 3,500 goes in here is harder than how many 35 goes in there, right? So what I'm saying here is, if you change only the divisor to the whole number, it gets so much easier. So writing this back here, 36,678 divided by 33.5 can be easily solved changing only considering to change the divisor to the whole number. How did I do that? I multiplied this by 10 and do the same thing here. Multiply that by 10. So you have 366.78 divided by 35. Okay, so try to change the divisor to the whole number. Then you can easily solve this. So let's do the long division. Divided by 35. How many 35 goes in 366? In 360, you have one of them. And subtract, and you get 16. Smaller than 35, so you have nothing there. But drop 7 there. How many 35 goes in 167? 4? Okay, so that is what? 4 by 20, 140, and subtract that, and you get 7, 2, 8 there. What is the closest? 8. What happens if I multiply that by 8? Too big?
Yeah.
7. Okay, so 5 times 7, 35. 3 times 7, 21. So something like that. You can continue until you can't do anymore, right? So that. You can keep going on and on and on. Okay, so again, if you have division of decimal points, try to change the divisor to the whole number by multiplying same power of 10 to dividend and the divisor. Because you can have the same division there. Think about the fraction. If you multiply same number on the numerator and the denominator, the fraction doesn't change. It's still equivalent. Okay? So let's do one more example there. This is too easy, so let's move on to this one. 75.45 divided by 3. We can do this, right? We can do this. So that's same as divided by 3. So you can just, divide it to find the answer. Okay, how about this one? We already know the answer for this one. Okay, let me write that down somewhere. So 75.45. I'm giving this to you as the hint. 75.45 divided by 3 is equal to, what was it? 25.15. Using this, can you solve this one? Oh, no, actually, we're not using that. I'm sorry. I thought we were using it. Okay, never mind. Can you find this division, the quotient and the remainder? Or just quotient? Try to solve it on your paper, on your notebook. What's the hint? You can change the divisor to the whole number. So when you're changing that to the whole number, by multiplying by power of 10, do the same thing to the dividend. Okay, so what's the first step?
You can give the decimals.
By how? You want to multiply?
You go 10 to the second.
Yeah, which is 100, right? So you're going to do the same thing. Okay, so we have 120.32 divided by 32. Right? This is easier than dividing by 0.34 because how many 0.34 goes in 1.2 is not easy for us, right? We can solve the problem easily when we are given the whole numbers. Now we can solve it. How many 32 goes in 120? 3, which is 96. Subtract. You get 4. 2 and drop 3 down. 32 times what is close to 243 or less than that?
You can't see that.
Oh, what happened? Okay. What goes in here? 7? Okay, 7. But remember, this is decimal point, so 3 is not, 3 is just 3, one whole number. That 7 is 7/10, right? So you need to line up the decimal point there. So how many, what's 32 times 7? 7 times 2 is 14. 224, okay? Subtract, and you get? And drop down 2, right? What goes here? 32 times what is closer to 192? 6, which is 192. Ooh, that's perfect. So 0 is the remainder. Your quotient has to be 3.76. Okay? All right. When you come back, I will, let's do more problems and then we're gonna finish this section. Okay, that sounds good. I will open the homework for this section, but it is not due until Wednesday, okay? Have a good weekend, guys.